Hey there. I'm Phil Lamar, and I want to welcome you to Ask the Astronomers Live, brought to you by NASA's Universe of Learning. Now, this is the show where we bring actual living, breathing scientists to answer your questions about the universe. And if you want to find out about upcoming shows and also see lots of fun astronomy videos, you can visit our website at universeunplugged.org. Hopefully, yeah, there it is, right there. You can see Universe Unplugged. Okay, today our topic is how do you make a photo of a galaxy? We're going to be delving into NASA's Astrophoto Challenges, which is a thing where it provides viewers, regular folks like you and me, a chance to take real astronomical data and tools and make beautiful pictures. And in the Astrophoto Challenge we're focusing on today, participants created these amazing images of the iconic starburst galaxy M82. Starburst galaxy, sort of like cosmic fireworks, which is appropriate with the 4th of July coming up, I think, right? And for those of you who, like me, are not familiar with the galaxy M82, fortunately, we have two people who are very familiar with it. Why don't we meet them? Let's first say hello to Sabrina Steerwalt. Sabrina, can you say hi to the people and tell them a little bit about yourself?
Yes. Hi, Phil. I'm Dr. Sabrina Steerwalt, and I am a professor of physics at Occidental College in Los Angeles. I'm an extragalactic astrophysicist, which means I study galaxies beyond our Milky Way. So we sit here orbiting our sun, a star, which is very special to us, but it's one of hundreds of billions of stars in our galaxy, the Milky Way. And our galaxy is just one of hundreds of billions of galaxies out there in the universe. And so I want to know how those galaxies got there, their histories, how they form, how they evolve.
That's so cool. And to help make things simple enough that I can understand them, we've got Sabrina, and we also have Robert Hurt. Robert, hello. Why don't you tell the little people, tell a little bit about yourself and show the people how brainy you are.
Okay, well, I'll at least tell about myself. They can make other judgments on their own. But I also am an astronomer. I actually work at Caltech at the IPAC Institute there, and my job is could be described as being an astrophysicist. I actually am responsible for trying to come up with visual ways of explaining science for part of our outreach and communications. And part of that job is actually taking astronomical data sets and trying to make them into the most beautiful, engaging, and educational images that we can put out there to share with you. And so I've worked on a lot of missions like NASA's Spitzer Space Telescope, the NEOWISE and WISE mission, GALEX, ongoing X-ray mission called New Star. So yeah, sort of making pretty pictures is part of my day job, as it were.
Ah, well, that explains why you're here. Now, with the Astrophoto Challenge that we're focusing on today, it's specifically images of galaxy M82. Sabrina, why is M82 particularly interesting?
M82 is a fascinating galaxy because it's been a sort of source of confusion for a while. It was dubbed an exploding galaxy because it has streams of hot gas coming out of its center. And the more astronomers looked at it in different kinds of light, we've learned more and more about it, and it looks like it's forming tons of stars. So it's this overactive stellar nursery in its core, forming stars 10 times at the rate of our Milky Way, which is no slouch to start. And we think this is because M82 has had a close encounter with one of its neighbor galaxies that has sort of stirred things up in its center.
Oh, wow. That's an exploding galaxy. That's amazing. Robert, now you were talking about part of your focus is imagery, which obviously the Astrophoto Challenge is about. Can you tell us in more detail about the Astrophoto Challenge itself?
Sure. So NASA's Astrophoto Challenges are actually an opportunity to sort of share the love and let everybody come in and do the sort of stuff that I do for my job, because there's nothing kind of proprietary about science data and NASA's data. We wanted to set up a scenario where anyone could come in who's just interested in astronomy, get access to actual observing data, the same kind of data that astronomers use to their research, and then give them access to the exact same, or some of the exact same tools that astronomers use to analyze their data, so that they can get this kind of real world experience of sort of demystifying what it's like to work in astronomy and to work with real research data. And as the cherry, the thing that we tease is, like, at the end, you get to make your own picture of a galaxy, and you get to share that with the world. And if you're interested, it can be the first step in really learning a lot more about how to dig in and really take your astronomy interest to the next level.
Wow, that's so funny, because I mean, to be super honest with you guys, I never really thought that making beautiful imagery was part of being an astronomer. I thought it was just a lot of math.
It's that too. In fact, there's a little bit of math that goes into making the images nice too sometimes. So that's part of the process.
Oh, well, that sounds like a good segue. Should we go take a look at the Astrophoto Challenge website? Because I would love to see some of the, we've talked about these beautiful images so much, I kind of want to see them. Oh, here we go.
So I'll jump in and set up this first one here for you. The first,
please.
The NASA Astrophoto Challenges was actually two different challenges, right? There are two different things that you could do. One of them was called the Micro Observatory Challenge. This uses a ground-based network of robotic telescopes that you can actually give your observing request to, and it will go off and it will collect data for you. So for the M82 challenge, people were able to go and schedule their own observations. Data came from the telescope, and specifically handed to them, and then they got to put that data together using these optical light sensors and make their own image of the galaxy. And as you can see, flipping through these pictures, right, there are a lot of different ways you can visualize these data sets, and they show off different aspects of the galaxy. And a lot of these are the same tools that astronomers use to actually dig in and understand what the data is telling them. So, a lot of
you can request. You said you can make a request.
You can. The Micro Observatory Network actually is available even outside of the challenge to you. And if you want to get involved and have a telescope observe data for you on anything, it doesn't actually even have to be M82. You can use this as a resource to go and get data on something you want to study and look at and make your own images for. So we'll put the URLs for this up for people later. But I think just flipping through here, there are just some great examples of what people have put together. And these images are actually really evocative to me, because they look a lot like the images I grew up with looking at M82. Really showing what in optical light, visible light, this actually appears. Of course, that's just one half of the challenge.
So, Robert, Sabrina, all of these images are the same galaxy. All of these different colors and all of this is the same galaxy?
Yeah. So if you, the other half of the challenge is NASA's photo challenge, NASA's Astrophoto Challenge, which here, as you're pointing out, this galaxy starts to look very different. And that's because we're looking at different wavelengths of light, but these are all the same galaxy. These are all M82. And so different wavelengths of light, so that's optical light, infrared light, UV, ultraviolet light. These are all showing different things in the galaxy shine at different wavelengths. And so we're looking at old stars in some cases, new stars in some cases, dust that's being heated up by the stars. And so this is an X-ray, like that picture we just saw. So you're seeing, so you're seeing really hot gas in the X-ray. And so you get the same galaxy, but very different perspectives. And using all of these different wavelengths, we can really piece together what's going on in this galaxy. Whereas if we just had, say, optical light, we wouldn't know the whole story. And so these are actual entries into NASA's Astrophoto Challenge, which takes data from space, NASA space telescopes, and then people can manipulate it using tools, NASA tools, to pick out the different wavelengths they want to look at, highlight different parts of the galaxy. So you can see these images are truly, truly stunning, and they're made by everyday users, entries in the participants in the challenge.
So that's incredible. So everything we're looking at is the same, but through different, I won't say, I was going to say filters, but not really, but you're sort of seeing it in a different way.
Yeah, you can think of it like an Instagram filter. I want to pick out this this kind of light. I want to pick out this kind of light. You can absolutely think about it like an Instagram filter.
Actually, I would jump in and say, like this image in particular, and some of them that we're seeing that have the more sort of Technicolor look. These are very equivalent to an Instagram filter, because they're ways of taking the brightness of an image, of a single grayscale image, and changing the brightness into different kinds of colors, and that brings out detail. It lets you dive in and see the detail more precisely sometimes. The other thing, though, that you can do is a lot of these color images are actually reconstructed full color images based on 3 different wavelengths of light from the spectrum. And this kind of ties into the way what a color picture really is. Like when you pull out your cell phone and take a picture, what that color image that you see on the screen is really 3 different grayscale images. Your cell phone has a detector that basically has some pixels with red, some pixels with green, and some pixels with blue. And when you take one snapshot, you automatically get these 3 grayscale images that your phone puts together and displays as a full color image. But with these other telescopes, right, when you're making an X-ray observation or an infrared observation, you're only doing it at one band of light at a time. You're not getting that automatic color image out. And so what the Astrophoto Challenge lets people do is go in and pick which 3 different channels of data they want to take, and they map those into red, green, and blue, and then you get a color image. I like to think of this like it's like translating. It's like translating a color you can't see in the infrared or the X-ray or the ultraviolet, and you're translating that back into the red, green, blue colors that you can see. And that's why these pictures look so different, because red, green, and blue can mean very different things from one image to the next.
Right. That's okay. That's great. And the difference between the Micro Observatory Challenge and the NASA Data Challenge is where the telescopes are, correct?
That's correct.
Yeah, for the NASA Data Challenge, you're pulling data that's out of it's in the science archives that are from space-based telescopes. The
Space-based, got it.
For this particular one, it was the Hubble Space Telescope for visible light, the Spitzer Space Telescope for infrared, Chandra X-ray Observatory for X-rays, and the GALAX mission for ultraviolet. But what's cool, though, is ultimately all of these data sets, they're actually in public archives that anyone is allowed to go in. And it's kind of our hope that setting up this kind of data challenge and letting people play with the same tools astronomers use, that if people get excited about this, we hope it actually encourages them to take the next step and learn how to use the archives, and they can make their own pictures. You don't have to work for.
I don't know. Be careful. They might come and take your job, Robert.
Yeah, so we put telescopes in space. I was going to say we put telescopes in space because for a few reasons, but one of the reasons is because certain types of light can't make it through our atmosphere. So like the ultraviolet light, you'll see ultraviolet light in the NASA Astrophoto Challenge, but you won't see it in the ground-based Micro Observatory Challenge because we have to put our telescopes in space to get that kind of light.
Interesting. Okay, so it's not just because when they're mounted on Earth, someone could be walking in front of it and block it. It's for different reasons.
And it sounds cool to put things in space. Another good reason.
And when it's on Earth, you only get to work at night when there aren't any clouds. Unless you're a radio astronomer, radio telescopes can work in the day and the night.
Keep going.
Even with clouds sometimes. So.
Right. Well, for anybody who's just joining us, talking with Sabrina Steerwalt and Robert Hurt about the NASA Astrophoto Challenge for the M82 galaxy. And these images that you're seeing here were made by not professional astronomers, but by viewers like you using real data from NASA space observatories and the Harvard-Smithsonian Micro Observatory Telescope Network. So anybody who's watching who has questions about these images, about M82, or just questions for brilliant young astronomers, Robert and Sabrina, throw your questions in the chat. Okay.
He called us young,
wait,
Robert.
I like it. I like this guy.
Well, because when you guys get old, you'll look like mad scientists. You'll have big fluffy hair and wear lab coats all the time. So obviously you're young. But we do actually have a question from the audience. Celsa Canedos asks, since galaxies are so far away and are them, I think every image from a galaxy is an important tool to learn and understand galaxies. Oh, so it's a statement and a question. That was the statement part. Here's the question. What are the most critical factors that an astrophotograph should have to be considered useful for science? That's a pretty heavy one. Who'd like to take that?
Well,
Sabrina?
No. Go ahead.
I would start by saying that when we look at these images, one thing that makes them right off the bat useful is the choices that are made to differentiate the different kinds of light, right? So if you'd made everything red or a different version of red, it would be harder to pick out. But the way these images have been made by participants in the challenge, you can right away see, oh, if this image is tied to ultraviolet, I right away know young stars emit in the ultraviolet, and so I can already pick out where the young stars, where new star formation is happening, because it's well differentiated in the image.
Yeah, if you use color to your maximum advantage to actually really be able to identify and call out what you want people to focus on, it can really succeed. And the other aspect of what makes that image useful is that the astronomy data isn't just a picture, it's actually also a measurement of the light. This data is calibrated, and so it's the image can really guide you into what's interesting, that maybe the ratio of one wavelength to another is telling you something about the chemistry of what's going on there. But then you can actually go in and measure the amount of light coming at the different wavelengths, and those direct measurements then can feed into your mathematical models of chemical processes and and from those we can start to deduce things like composition and temperatures and things like that, and really dig into the properties.
I see.
So it's not just a picture; it's numbers too, and the numbers are
well. It's funny because when we first started talking about it, it's like, well, you're taking astronomical data and making pictures, and when I first read that, I'm thinking, is that like in the old days when you had elementary school computer class, like, I'm going to make a 3 out of 3s. Is that making an image out of data? But what you guys are talking about is on a whole other level. But I love that. I hope, Celsa, I hope you felt like that answered your question about what makes something useful for science. Oh, we have another question from the audience. From Rachel Zimmerman Brockman. How can students get involved in future opportunities like this?
Well, I'll jump in and just say that, for one, the existing NASA Astrophoto Challenges are still up and running. So, at the end of this, we'll put up the URLs, and you can still go and you can still do these and make your graphics for M82 or some of the previous challenges, the Whirlpool Galaxy and the Lagoon Nebula. But in addition, there won't be any more Astrophoto Challenges this year, but if you check back next year, we're going to be spooling up some more. And so there'll be another chance to actually jump in and do one and submit your work and sort of hopefully get it out and displayed like we did with some of the featured pics from the previous years as well. You can get to on the site.
Now, were there any pictures that people made that you guys didn't put up because they just picked 3 sets of data that were all black? And it's like, guy, I can't see the galaxy at all now.
I don't think anyone submitted anything like that. In fact, one of the things that we really wanted to do is make sure that everyone felt that they could and should submit their data. And I think a lot of people we know played around but never actually submitted an image. And we really just want people to feel empowered when they do this. And there are no wrong answers on how to make an image. I mean, things can work on a static level, they can work on a scientific level. But I think we got over 300 submissions this year, so we didn't have time and room to put all of them up. So we sort of went through and picked out like highlights. But I think everyone should really want to submit and compete, and it's not really a competition, but
because there is no prize. except science. Wait, oh, is this another question? Yes. CP asks, what can different wavelengths tell you about an object in space? This sounds like we sort of touched on this briefly before, but what can different wavelengths tell you about an object in space?
So
Yes,
different
Sabrina?
wavelengths, different things in a galaxy or an object will shine at different wavelengths. So for example, stars shine a lot when they're older, they get redder. So they shine more at longer optical wavelengths or even in the infrared. Young hot stars will shine more in the ultraviolet. So when you see what's emitting, you know, where you're getting more emission from, it tells you about what must be in that galaxy to do that emission.
Yeah, when you say shift into the infrared, I've done a lot of work with infrared data from Spitzer, and what's interesting is things that in visible light are opaque dust clouds that block your view. Actually, they become transparent, and so it lets you see to things that you couldn't see before. You're actually seeing through the smog to get to more distant things that were obscured. And if you go far enough into the infrared, that dust itself begins to glow. And so you actually start to see the dust instead of the stars. And so, you know, each one picks out a different part of the structure. That there's far more to a galaxy than it's not just the stars. You know, there's the gas and the dust and all these things. And you need the whole ensemble to put it all together to get the complete picture.
See, now that's so funny because I've heard in these discussions people talking about dust in space, and that always sort of puzzles me. It's like, is it literally dust, or is dust a sort of astronomer term for something else? That's a question from me.
That's allowed. That's allowed, right? It's dust. Well, it is. You can think of it like dust. A lot of the stuff that's doing the emitting in M82, showing this huge outflow, is something that we call polycyclic aromatic hydrocarbons, which is kind of a mouthful. So we say PAHs, PAHs, and it's kind of like soot. It's not that different from the stuff that's in your barbecue pit. And so it's dusty, junky stuff that, much like if you had a really dusty window, you couldn't see out of it. Robert was saying when you have dust in the way of your starlight, you can't see through the dust to the starlight always.
Interesting. Okay. We have another question from our live audience, which, yay, that means that people are actually watching and listening to us. This question is from Space Time with Robert. A different Robert?
I swear I did not ask this.
But the question is, what's the easiest galaxy in the northern hemisphere to photograph other than Andromeda? That's an interesting question.
I think Sabrina and I are both very used to using deep space telescopes, and we don't think about the hemispheres so much. But from my days as an amateur astronomer, when I used to drag my 6-inch reflecting telescope out into the backyard, in the winter nights, I would say the one I probably had the easiest time getting to, other than Andromeda, was M81. This is actually the companion galaxy to M82. It's very close. It's another bright spiral, and I think it's like an Ursa Major, if I'm remembering my amateur astronomy correctly. So
interesting.
And do you have any favorite northern hemisphere galaxies, Sabrina?
Well, I was going to say that you should be able to. I don't know about easiest, but you should be able to see M81 and even M82 with an amateur telescope. Oh. If you have,
where do the name?
You're in Los Angeles, you need to go.
Yeah, that's too much. Where do the names M81, M82 come from? Again, another question from me. Sorry, guys, I'm hijacking the whole conversation.
Yeah, so
I need to know.
I can answer that. The M stands for Messier, after a French astronomer who made a catalog in the late 1700s. And he actually only cared about comets. And so he was just listing all the stuff that wasn't comets that he didn't care about. And so I think he listed something like 103, and then other astronomers added a few. So I think the total is 110. what we call Messier objects, or M something. And some of them are galaxies, but some of them are not. Some of them are clusters of stars in our own galaxy. And so you have a range of things. It's kind of an odd catalog because it's a range of things, but it was things that were really bright that you could see in the late 1700s that were not comets.
Wow, that's
and
so
I think
funny.
that's why it's such a common name, because these were the brightest things you could get to in the northern hemisphere, and so it becomes that a very easy list of things to get to. There are other terms we use for galaxies, like NGC, which is just the name of another catalog. We tend to name things after catalogs, and they're.
I know there's no like Sabrina or Robert.
Well, no,
actually,
those are saved for
named after
hurricanes.
The lead author on the paper was too. Yeah.
Right. Well, I love the idea of Messier objects, because in Canada that's just called a hockey puck. We have one more question from the live audience. Ashley Rodriguez, who's joined us here today, has a question. She asks, in your experience, have you had a favorite galaxy that each of you have studied? And if so, why is it your favorite?
Well, I'll jump in. I absolutely do have a favorite galaxy. It's called Messier 2, which is actually named after an astronomer who was a Italian astronomer, and he discovered a fuzzy thing right down in the murk of the Milky Way in the early 1970s. Turns out it's a relatively big spiral galaxy that was missed. And it's because it's behind all of that dust that's in our own Milky Way galaxy, those dark lanes that you see in the night. And as such, it was actually missed by generations of astronomers. If it had just been located a few degrees further south, it would have its own Messier number. But because it was kind of hidden, it took it was really relatively unstudied by the time I was in graduate school. So I did a lot of work in infrared and the radio studying that galaxy, because at those wavelengths you could see through the murk and actually observe what was going on. And thematically, Messier 2 is also a starburst galaxy. So that's where I got interested in starbursts, with a lot of gas funneling in, the big burst going on right in the core. So that is totally my favorite galaxy.
Messier 2. Sabrina, what's your favorite galaxy?
Well, one of my favorite galaxies, I like small galaxies. We call them dwarf galaxies. That's the official term. So much, much smaller than our Milky Way. And one of my favorites is a galaxy called Hanais 210, which has, again, a lot of stars forming, a lot of bursts of stellar activity in this tiny little galaxy. And it's one of the first dwarf galaxies that we've found to host a massive black hole, which is very exciting. Yeah, because we don't know very much about black holes in these smaller galaxies, massive black holes.
Wow. Massive black hole, small dwarf galaxy. That sounds like a dangerous combination.
Yeah, it is.
Actually, right? We have a couple of questions that were pre-submitted that I'd love to get your guys' responses to. And these are not submitted by me.
Actually,
but
these I believe
they are things I'm wondering
by participants in the Astrophoto Challenge, because they were actually invited to ask questions when they put their images in. So we can finally get a chance to get back to some of them.
Yes. Hey, people who submitted to the Astrophoto Challenge, here's your prize.
Oh, wow.
And this first question is from Shiva M. And the question is, what galaxy shape is M82? Oh, and it's apparently a multiple choice question. Is it irregular, spiral, or elliptical? Robert, do you want to take this one?
I can jump in. So when I grew up, we always called M82 an irregular galaxy because it looked so weird, because it had all this weird stuff and it was exploding. But I think we more or less understand now that it's a spiral galaxy that's got a nuclear burst going on, but we're seeing it from the edge. And that actually disrupts our view of the disk. And because the thing we really noticed at the streamers, that gave it its irregular category. But in fact, we do reserve the term irregular for different classes of galaxies, ones that are really disrupted and don't have a clear morphology. But there's a good chance if we could see M82 face on, we'd probably see some spiral arms and things going on in its disk.
Wow, that's interesting, because our evaluation of what the shape is of course based on how it looks to us, right?
Mm-hmm.
Yes.
Now, Arturo Q has what's basically sort of a follow-up question. Why do galaxies look irregular? Is it related to a galaxy's age or evolution stage? Sabrina?
So galaxies, sometimes they look irregular because of something that happened in their history. Like M82, we think one of the reasons it looks so different and irregular is one, as Robert mentioned, we're seeing this spiral disk from the side. But also, we think it had an encounter about 100 million years ago with M81. And so when galaxies pass by each other, the gravitational pull, they sort of have a little tug of war, and that disrupts what's going on in the galaxy. And so we think that created this starburst, all this prodigious new stars being born in the center of M82, and they're having violent stellar winds that are throwing out all this gas that we're looking at. So certainly we think this irregular shape for M82 comes from that. But being an irregular galaxy isn't necessarily a stage of evolution that every galaxy is going to pass through.
Interesting. Okay. That's good to know. So it's less about it's not like being 13 and getting zits. It's something that happens that can cause that irregular shape.
Often, yeah.
Often. Oh, interesting. All right. We have another question from Rohan C. How is it that subtle differences in how an image is taken, like X-ray low versus mid versus high energy, or near versus mid infrared, can make so much of a difference?
Yeah, so we mentioned a little bit about how different things emit at different wavelengths, and that's obviously an ultraviolet, something way on one end of the spectrum is going to emit you're going to see different stuff than at the radio wavelength and longer wavelengths. But even within the infrared, near infrared light, you tend to see you don't see dust, but you see older stars. And just moving a little bit redder, so a little bit longer wavelengths into the mid-infrared, then you start to see dust being heated up by those stars. So it all just depends on what's doing the emitting, what's shining at those wavelengths.
Interesting.
Just
wow.
toss
Hot
in
dust.
one other idea there too, is that, if you go to the fruit section in your grocery store, you see red oranges, red tomatoes, yellow bananas. And those are all very, very close in wavelength, but when you get really close in wavelength, there can still be differences in chemistry. Different materials interact differently with light. And so everything you see in the world around you that has distinct colors is actually going on because the material interacts differently. And that extends beyond the visible spectrum as well. Each different materials can have different reactions to very specific parts of the spectrum too. And that's all part of the magic for how we can figure out what's going on out there.
Excellent. All right. Let's see if we can get a few more questions in before we have to go. Here's one from Ji-Yun Y. Where does most of the star formation occur in M82? Hey, we're back to M82. Let's not forget who the star is. Oh, wait, can you call a galaxy a star? You know what I mean. But where does most of the star formation occur in M82? Robert?
So I think we've kind of hit there, but it's actually happening in the center. And one of the reasons we know this is that when you actually look at what's coming, this so-called, these streamers, you can literally see they are streaming away from the center. So when you move into certain wavelengths of visible light, and specifically when you get into the infrared and into the X-ray, the whole conical structure of what's coming out gives you the clue that has to all backtrack into a single point. If it was happening all across the disk of the galaxy, it would actually look different in the infrared and in the X-ray. You would see, it wouldn't be coming you wouldn't see a conical shape with radial fingers. You would see things streaming up like that. So we don't make it up, right? It's all part of that process of looking at it at all the different wavelengths and then analyzing what processes could result in creating the structures that we see. And then that's how we deduce that the center is where the action is in this one.
Excellent. That's good to know. And still, M82, we want to know what's next for M82. Sabrina, what is the future of M82? Oh, Nino G wants to know, Will it merge with M81? Okay, Nino, here come your spoilers.
Well, spoiler a few billion years ahead of time is that yes, it will. We think it will merge with M81 eventually. So we can see the havoc that has been wreaked by the gravitational tug of war when they made their first pass, at least one pass 100 million years ago. And so in a few billion years, we think they're going to pass again as their gravitational pull pulls them towards each other. And then that will be a much more direct hit at that point. And then we'll have the fireworks of a merger.
Maybe a starburst in M81 too.
Yeah.
Wow. So are you talking a galactic collision?
Yes.
Wow.
Yeah. Pretty exciting stuff. And you know, our Milky Way will eventually collide with Andromeda. So another spoiler.
Wow. So you're saying I shouldn't invest in real estate. Okay, good. We'll
have other issues before that happens, like the sun reaching the end of its lifetime. So it's
good point. Planning ahead. Wait, we have another question from our live audience, from Rachel Zimmerman Brockman again. Hi, Rachel. Thank you. And this is a great question for you guys. What's your favorite thing about being an astronomer?
Well, I am the kind of astronomer that takes observations. And so sometimes that means using NASA telescopes. I don't travel to those telescopes, but it also means traveling all over the world to go to telescopes on the ground and getting to meet interesting people in lots of remote corners, and, you know, getting to point $1 billion pieces of equipment where I want it to point. That's pretty cool too.
Robert,
I would say that just the fact that we have the capability, just sitting on our planet, launching a few things into orbit out around the Earth and Sun, we have this capability of like the ultimate CSI mystery of how did the universe be, right? And that just in the course of my professional career, so much has changed in our understanding and advanced. And not that we've like thrown out the Big Bang or anything, but we've learned so much more about the processes happening immediately after. We are starting to see there's some weird consequences for what the future of the universe may be that's totally different than we thought before. And for me, it's just this chance to constantly have the opportunity to just learn these mind-bending things that we really are solving these cosmic scale mysteries, you know, and year after year after year. So just between whether it's discovering planets on other stars or the ultimate fate of the universe, right? All of this has happened during my career as an astronomer. So yay.
There you go. That sounds like a pretty amazing thing to have as your job. All right, gosh, we're almost out of time, but before we go, do you guys have any closing thoughts, that things you want to say to the folks who are watching? Sabrina?
Sure. Yeah, I would just like to thank all the people who participated in this challenge. I think it's really great that people are taking an interest and spending time getting to know the data and working with it themselves, because the sky belongs to all of us. This data belongs to all of us, not just you know, some nerdy astronomer sitting in an office somewhere, windowless office usually. I am so glad that people are getting their hands on this data, and I encourage people to do it more, because yeah, the sky is for all of us.
Wow, that's ironic that astronomers have windowless offices. Robert, closing thoughts?
So, well, I actually prepared one. I actually brought something for show and tell today because it partly kind of an inspiration of all the fun work people had on finding not just scientific but artistic and creative ways to display their data. I put together a little something last month myself, my own submission to the M82 Astrophoto Challenge, if you will. I actually took the data sets from 3 NASA observatories and sort of arrayed them of the same slice, the exact same slice of the galaxy, starting in the infrared from Spitzer, visible light in the middle from Hubble, X-ray from Chandra at the end. And I sort of used the pride flag, the colors of the traditional pride flag as a way of displaying this to, for me, this kind of encapsulates a lot of what it's all about in astronomy, and how astronomy can maybe be a good metaphor for our lives in general. Like when people say, well, what good is it to learn this stuff if, how do you apply that to your everyday life? I feel like a picture like this of M82 shows that if you were to just look at the universe through one perspective, one wavelength of light, the picture you get of what's going on there would be so vastly incomplete compared to what you get if you actually expand your view and take in every diverse way of looking at the same object. Every perspective adds a new dimension of what's going on there. And then when you put that all together, you can finally maybe get at a better understanding. And if you want to take that metaphor and extend that onto your life, and please do. But otherwise, happy Pride Month, everyone. Or I guess tail end of Pride Month. But
right, exactly. No, but that's such a great sentiment and a beautiful picture. Now, if people want to make their own images of M82, like you made that one, where should they go?
So if I think we can pop up a URL for people, and I think we'll paste it into chat for following it. But if you go to the NASA Astrophoto Challenges site, you can go to microobservatory.org/OWN/astrophoto. And from there, you can get to the microobservatory network that gives you access to robotic telescopes that you can actually either you can go to the archival data, some of the data that was already used for the Astrophoto Challenge, but you can even put in new requests to have it go and observe things on that you want it to look at and get that data and work with it. So that's part of what you can get there. I'll let Sabrina then cover the other things that you can cover when you get there.
For the other things that you can cover at the NASA's Astrophoto.
Sorry, the NASA Data Challenge.
Yeah, so you can look at
the basic. Right, microobservatory.
Right. So you can look at they post a new one every year with a new highlighted celebrity galaxy, maybe instead of star galaxy. And so you can wait for next year's new one, but you can also take a look at all of the data that's been from previous challenges and get your hands on that as well.
Excellent. All right. I want to thank Dr. Robert Hurt and Dr. Sabrina Steerwalt for joining us to talk about the NASA Astrophoto Challenge and Starburst Galaxy M82. And I also want to thank you guys for joining us to learn all of this stuff and to celebrate the images submitted by regular, everyday science enthusiasts like yourselves. Because if you're tuning into this, you are a science enthusiast. Just so everybody knows, and Sabrina and Robert, you can tune into this one too. In our next chat, we'll be talking to 2 different guest astronomers about 3D animation that lets you fly through space, through the Orion Nebula, which is a famous nearby stellar nursery. Stellar nursery, I guess that's where stars are born. Sorry, Lady Gaga, we're not talking about you. You can all check that out in the link in the comments. And you can see a recording of this chat, and Robert, Sabrina, you can send your parents to watch a recording of this, as well as all of our other videos at universeunplugged.org. Okay, that should be right there on the screen. You see it, Universe Unplugged. All right, and subscribe on YouTube. Follow us on Facebook so you won't miss any of the shows we have coming up, because we have other great fun stuff just like this. Until next month, I'm Phil Lamar, and you have been watching Ask the Astronomers Live. Thanks for watching.